All right. Let's try this again. Oh god. Unbelievable. All right. I don't even know where the. Here we go. Okay. Let's see. Does this work? Can we like actually do this? Is this cool? Is this neat? Aha! Here we go. All right. Cool. We're back to it. So, I think we're good. Uh, let's see. Okay. So where the fuck were we? We have been. There was a long conversation chatting. Thanks, Kobe. About Rust versus Julia for research code and like whether it's a good thing. I'm gonna preface this with we want to do this anyways, so this is kind of like a cheater's method of doing it. I'm just gonna live stream it. Maybe we get it done today. Maybe we don't get it done today. Um, but hi Nico. Oh wow. Okay, cool. This is neat. Like we actually have people coming in. I never know what like who's actually coming to these things, so it's always very weird. But okay, so anyways, very quickly, like long conversation about Julia versus Rust and all sorts of stuff for research code. And Rust is very cool. Hopefully, this will show a little bit of why Julia is actually kind of neat for this type of stuff, especially for benchmarking and quick release, code that's supposed to look a lot like the math. Um, and to do that, we are going to code one of the papers that Alex Nico, actually, who's in the chat, although he cannot hang around, and I published not too long ago, I think end of last year. So, very quickly, maybe let's start with what is ZODA. ZODA is a weird protocol where essentially what do we have? We want to essentially take a block. Block is just like, let's say it's a matrix of a bunch of data, and we want to encode it, so we want to encode the rows and then the columns. In other words, you stretch the block down and then we encode the rows. And in so doing, we get a bigger square. This is useful for a number of applications. I'm not super going to get into it why, but things like Celestia does this already. Things like Ethereum are planning on doing this, and so on and so forth. And then with this bigger block, what you can now do is people can take subsamples of this block. So they can take, for example, some number of rows or some number of columns. And across enough parties, the idea is if, for example, let's say across everybody, we have 50% of rows or 50% of columns. I think there will be a recording available. I hope there will be a recording available, although I am not recording. But I think it will be available through Twitter as well, so it should be good. Anyway, so we have this, block. If people sample enough rows or sample enough columns, let's say 50% of them collectively, then in spite of the fact that not everybody has every part of this big encoded block, we can actually recover all of the data that was in the original block that we cared about before we encoded it. So this is useful for a number of things, namely data availability. In other words, proving that you have indeed published a piece of data and that it has been made available for people to read or download at some point in time. Okay, so anyways, the paper here essentially shows how to achieve that in a way that isn't only, just doing this encoding, but the problem with doing this encoding is, let's say everybody gets a bunch of shares, so they get a bunch of these rows and columns. They need not actually know that the rows and columns correspond to a true encoding of the object. So that's a problem, because if you have a malicious person coming up with these rows and these columns and, is trying to do all sorts of stuff, they could just send you random nonsense and claim those are the rows and the columns of the true encoding. So zero overhead data availability essentially, or ZODA, shows how to do that. In other words, how like you can turn these rows and columns into essentially ZK or succinct proofs of their own correctness, which is like kind of neat. So essentially what it tells you is like normally the way you would prove it is you would take a small block, you would encode it, and then you would stick it in some, for example, like a ZK VM. So you could stick it into RISC-0's VM or succinct's VM, and then prove that you have indeed computed these operations, you have done these encodings correctly. That's very expensive, right? Often the proof is like thousands of times slower than performing the operations themselves, which is like not great. It turns out that by virtue of the fact that we are kind of doing these encodings already, that's most of the way towards a proof that they are correct. And that's the idea that we exploit here in ZODA, and in turn, what will let us kind of do real-time proving, quote unquote, of these encodings of these blocks without needing to do all this like overhead of taking, this encoding operation as an abstract thing, putting it into like a general purpose VM, and then afterwards getting a proof that everything we did was correct. Okay, sorry, I'm like kind of super not used to doing this and just like saying stuff out loud like this, so at least not without an audience. So, okay. So, with that, so this is the paper for anybody who's interested, would recommend reading this. It's not just also about encoding. It turns out that if you do ZODA kind of for free, you also get what's called a polynomial commitment scheme. And you get for free verification of such a thing. So not only do you get that like this matrix is encoded correctly, you also go most of the way towards a proof of some computation happened in this block that you cared about and it was correct, which is cool. I'm not going to go over this. This is not super immediately interesting. Just know that like as a side effect of kind of implementing this ZODA protocol, you for free can also like proof stuff in a block, which is like kind of sick and cool. And I rant about it in some like blog post or whatever, but it's not super interesting right now. Okay, how are we going to do this? And why even do this in the first place? Well, number one is we had a long conversation about Julia versus Rust. And it's a funny thing to have a versus for languages. It doesn't really matter. The point is, like, Julia is just actually quite nice for writing ZK stuff. Specifically, if you want to make it fast, or if you want to make it relatively performant, you want to do benchmarks on it in like relatively minimal code. And not only that, to do it in such a way that it looks like the mathematics of the paper. So we'll hopefully at the end of this, we will see that like you can look at the math of the paper and you can look at the code kind of side by side, and when you read through it, right, they will look relatively similar. So we'll be, for example, in ZODA, we define these matrices. Let me just zoom in here really quickly. We define these like matrices x tilde. We do these encodings. It'll look relatively similar to kind of what this shows. We won't actually do this algorithm. We'll actually implement the algorithm in tensor variation here. So this is a variation that does not have zero overhead. It has negligible overhead relative to doing the encoding, but it's just more efficient in practice. And to know why, you just can take a look at the numbers down here. Roughly speaking, it essentially enables smaller nodes to get the proofs, whereas ZODA itself requires bigger nodes, even though it has lower overhead. So, cool. Okay. That's the high-level idea. Hopefully everyone's cool with it. If you aren't cool with it, I'm sorry. You're going to have to deal with it. And yeah, let's, I guess, quickly get started. So I have no idea what my last thing is in Visual Studio Code. Also, why is there like drilling or something going on out here? Okay, that is a paper. So let's just start a new project for fun. Also, please let me know if this is actually visible, by the way. It would be super cool. I am actually not really looking at the stream, so I should do that. Let's see. Oh no. Thanks, Kobe. Where's the chat? Oh, interesting. I can't see all the older stuff that happened in the chat. I am so sorry. Okay. Hopefully, people haven't been, people have mostly been behaving in the chat. I realized for some reason it doesn't display everything that's happened prior. So that's cool and very good to know. Okay, so let's see. Code. I'm just going to start a new Julia project. Oh my god, there's so many things here. Here we go. No rush. Okay, no rush to what? Sorry guys, I realized because I didn't have the chat out, anything that happened between essentially when I started the live stream and said the 3 things and then afterwards has been completely erased, which is super neat and cool. So if you have any questions or you have any things you want to say, just let me know again so I can go reread them. Okay, so let's just start. So how do we do it? Oh yeah, so I guess getting things set up at a high level point. I mostly just use the Julia REPL, although I guess I will show it in a second, but and Visual Studio Code with Vim key bindings. I have Copilot, I guess, enabled. At some point I should actually, learn to do the cool, sick vibe coding thing. I'm very normie and very boring in the sense. And if anybody has any tips for actually how to use AI during coding and stuff in a non-trivial way, that would be amazing. I will take anything I can get. Okay, so I actually have an old version of Julia because I haven't updated this thing in a long time, but let's say we want to, so this is, we're in Julia here. Let me hopefully zoom in a little bit, which hopefully helps. Oops. No. Okay, I actually don't know how to zoom in Ghosty, but we can go into the package manager by clicking the right square brace from the Julia REPL. You can then type whatever you want. So here I typed question mark, which outputs the help file. And essentially what I want to do, well, it would be cool to make a new package, which essentially I can type as generate, and let's call it, ZODA tensor. Yeah. So, and this will create a new folder with a package called ZODA tensor, which we can see here. And cool. And so I'm now gonna do the cool thing where I'm gonna open this in, Visual Studio Code. And if we do this, we get, well, let me actually switch to my Julia profile here. We get what we need. So we get a module called ZODA tensor, which has a function called greet, and it just prints hello world. So first things first, what I would like to do is I would like to make sure that I am in the right environment. So the module, so when you're in the folder, you actually are in an environment, much like the has some dependencies and stuff. They're just make sure they're all loaded, or at least known to the REPL. So let me activate this environment. Okay. There we go. So now we're activated in the ZODA tensor package. Let me make this at least a little bit larger so people can see it. And then, I can do something like using ZODA tensor which will bring the package into the namespace, and then I could do something like, ZODA tensor dot read or something, and that will print hello world. Okay, so that's cool. Sorry, it took a long time to actually get set up on this, which is very dumb. So let's start with some stuff. So we have this package, which is super neat, called cryptoutility.jl. So let's add cryptoutility.jl is actually made up of a bunch of sub packages, right? So we have batch Merkle tree, finally, binary fields, binary sum. I know I am really doing it. It's shocking. So let's start with binary fields. So just for fun, this will do the things that we expect. Just it'll download the package. It'll do all sorts of nonsense, whatever. Okay. And for now, we could do things like, using binary fields. So what does this package actually do? This package contains a bunch of neat, cool, interesting operations. So the simplest way to kind of explain that is, okay, cool. Let's say we have, so binary fields, how are they defined? A binary field is a binary polynomial. In other words, a polynomial which has zeros or ones as coefficients, modulo some irreducible polynomial. So how is binary fields built? Pretty much exactly the way you would expect. If you look at binary fields, we literally start with binary polynomials, which we just define a bunch of, this is like only 182 things. Just define a bunch of types and say, cool, number one, a binary polynomial, this is just a macro that does this stuff, is, a uint8 is a binary polynomial of degree 8, a uint16 is a binary polynomial of degree 16, all the way to 128. And then LLVM supports 256-bit binary polynomials. Julia does not inherit that support, so for a 256-degree binary polynomial, we just represent it as a tuple of 2 uint 128s or whatever. Let me zoom in here because I assume it's actually probably pretty small for people. Okay, so that's cool. We have a bunch of obvious similar operations, right? So we could say things like, please convert a binary polynomial to another binary polynomial of larger size. What does that do? That simply just casts the underlying variable to do the right thing. We can add binary polynomials together, which is simply take the XOR of the binary values and then get the new binary polynomial. We can left shift and right shift binary polynomials, which just says take the binary value, left shift it, and right bit shift it. And then you can join binary polynomials. So if you have two binary polynomials, say each of degree 32, you can join them into one big degree 64 binary polynomial. This would be useful for a number of reasons. You then just have these type definitions, which just say like, cool, the double, what's in which binary polynomial do two binary polynomial 8s fit? Well, it's in 16 and 32 and so on and so forth, and then the half types. These are just useful for defining things like join and split. Okay, that's cool. We can do things like shift upper bits, which essentially says, please take a binary polynomial 64, shift it all the way down, and then the real meat and the only meat, I will say, of this entire thing is this multiplication operation. So what you'll see is, so first of all, Julia is like essentially ahead of time / just in time compiled language. Which means that we can do this cool thing where we essentially inject LLVM code directly into functions as they are running. So most processor architectures have ways of multiplying binary polynomials fairly quickly. This operation in ARch64, which is like Mac M1 or like iPhones or Cortex A57s like the Raspberry Pi or anything like that. That operation is a ARch64 extension called pmul64. So pmul64 will take in 3 arguments. You can see this here. So it returns 1 argument and then it outputs. So it takes in essentially 2 arguments, not quite, but in here it's like represented as an n tuple of 16 of 8-bit things, but whatever. The point is it takes in 2 64-bit polynomials. So in other words, degree 64 polynomials that are over a binary field, multiplies them together, and then the output is a degree 128 polynomial. That's pretty much all that's happening here. And then what's going to happen is this function, every time we literally call we say, please multiply two polynomials, it will actually call this literal function. And by doing that, it will inject the LLVM call directly in where that multiplication is. And we'll see that in a second, what I actually mean. Like, we can make this very, very explicit. Cool. So that's multiplication up to the degree 64. For degree 128, you have to do fancier multiplication. Essentially, you do Kurotsuba multiplication, and that returns a binary polynomial of size 256. And finally, we have, some other multiplication stuff, some remainder stuff, and some EGCD stuff, which we'll use for inverses and all sorts of nonsense. Okay, so I'm going to make it very concrete what I mean when I say, like, we are actually literally, like, injecting these instructions. So let's say we have a bunch of binary poly 64s. Right, so, I don't know, let's make this like 0x02 or something. And then, I don't know, let's say just another random. Okay. So when we write A times B, right, this like returns what you would expect, which is a binary polynomial of degree 128. This is neat and very cool, and it seems like there's a bunch of magic going on, but actually literally what's going on, you would think from, for example, this code, which looks relatively complicated, what you're doing is you're doing like some thing, you're unwrapping it, you're then calling some operations or whatever. But if we actually literally look at the code that Julia spits out for this, because again, Julia is a compiled language, you can see that the LLVM code literally says right here, please load the first value, namely A, into the first register, and then the first double word register here. And then similarly, please load the second value here too. Right? And then please call the operation known as pmul, which is multiply the two polynomials in hardware, and then store the result of that in a quad size register, quad word register. And yep, that's pretty much the only thing that happens here, right? So like, the binary polynomial 64 is like a wrapper type around uint, but the compiler is smart enough to recognize that that's all it is. And so when we do this type of stuff, we don't actually have to like make pointers to the structs or whatever, all sorts of nonsense. Okay, that's pretty easy. We can also see that like if we do A plus B, that actually also compiles to the obvious thing, right? Which is please load the two things and then take an exclusive OR of the two and then just return that value. Okay. So I'm just giving kind of a weird intro to all of this stuff. The next question is, okay, those are binary polynomials. Can we do it over binary fields, binary elements? Yes. So let's do binary elements. And let's say binary element 32. This is one of the ones we're going to use. Oh my God. And let's say we do something like A times A. So you can see that, first of all, binary element 32 really is also itself a dumb struct. It is a wrapper around a binary polynomial 32, which says, look, this binary polynomial should be reinterpreted as a binary element. That's cool. Point number two is, once that happens, binary element 32, right? Like all it is just like says, cool, take a binary polynomial and take it modulo some irreducible polynomial, which we specify in the code. So when you do that, you get this like cool thing that says, okay, what are we going to do? Well, when we multiply two binary elements, we multiply their underlying polynomials, which gives us a degree 64 polynomial generally. And then we're going to reduce it modulo some irreducible polynomial, which is of degree 32, which then gets us back to a binary element of size 32. Okay. And we can, of course, as before, look at what the code actually looks like from here, which is neat. It's really very simple. It loads the two things. It then does exactly the same thing that it did previously. It then multiplies the two underlying polynomials, and then it performs a bunch of reductions, which is pretty much what you would expect from needing to do, binary polynomial reduction. Okay, so that's cool. If you're a nerd, hopefully this was at least like quite exciting. If not, then we'll get to actually coding ZODA in about 2 seconds. Okay. Another reason why Julia is very nice is you can do things like, okay, cool, I would like a vector of, binary elements 32 or something, right? And you can do like 10, and then that is a perfectly reasonable thing to ask for. You can then ask what's the inner product of this thing. So A prime is a transpose. This is like the adjoint stuff we were talking about. Therefore, A prime times A actually means something, and it's an inner product. You can, of course, also do a random matrix. So, and I haven't defined any of these operations for what it's worth. These are all just implicitly defined by the virtue of the fact that, like, binary elements have certain properties. So, let's say 2 to the 12 and 2 to the 10 or something, and then you can do like A times little a, and you get exactly what you expect. So, we created a matrix here, which is of appropriate dimensions. We can then multiply that matrix by the vector and get exactly what you expect. And it's pretty fast. So we can also benchmark what that looks like. And, you know, you wait a second, your computer heats up a little bit. Things happen. And at some point or another, this will spit out a nice, lovely plot that says, cool, doing this operation took you roughly minimally 6.2 milliseconds. The median time was 6.5. The standard deviation was 126 microseconds. You had no time in GC, and the memory estimate number of allocations took was about, 3 allocations with 16 kilobytes total of allocations, which is what you would expect, because that's roughly the size of the vector A, right? Which is 32 bits divided by 8 times length of A, which is 4 kilobytes, I guess. We probably end up allocating some more in other ways, but okay, cool. Let's see, has anyone said anything else? I don't think anyone is saying anything in the chat yet. Okay, so we have pretty much all the ingredients we need to start coding ZODA. So what is ZODA? At a high level, what we're going to do is we are going to take a matrix. Let's call it, for now, x tilde. I'm just going to write this as like complete pseudocode. So it's going to be x tilde, and then we're going to encode it. Rows. Let me just do it here. To get x. So that's going to be a new operation. So this is, and then we're gonna, then we're gonna commit to rows and columns of x. Okay, so this is the prover commitment. It's gonna be this. So we're gonna commit the rows and columns, we can get x, we're gonna commit to the rows and columns of x. So, out is gonna come like 2 Merkle roots. Okay. The proof. So the prover actual proof, oh shit, that's a good point. Let's move that. I'm gonna move it over here because it feels like the right version, right part. Hopefully this is, let's move that, doing something here. Aha, there we go. Okay. Thank you for letting me know, by the way. Okay, so, so what's the actual proof? Right. So in the proof, the prover is going to receive some randomness, which it's going to be from Fiat Shamir, but could be anything. And then it's going to simply compute x tilde transpose, x tilde times randomness. Let's call this R and R prime. Then X, it is going to compute this, so it's going to output what's called YR, and then it'll also output, which I think we call it WR prime in the paper, which is going to be X tilde transpose R prime. And let me just make this assistant R prime. Okay. And these are going to be the proofs that are relayed to the verifier. So that should be, so let me just make sure I am, again, like looking at the chat. Okay. So these are, so the Merkle roots are what's going to be relayed to the verifier, and then these random linear combinations are going to be relayed to the verifier as well. So that's pretty easy. And this is, in reality, what actually is going to be what we're going to call the non-interactive part of the proof. So the randomness here, we're actually in a real ZODA protocol, in general, we're going to get from Fiat Shamir on the Merkle roots. The next part will actually be interactive randomness. So cool, I said like, okay, what are people going to do? What do people normally do in data availability? They're going to sample some rows, some columns, and then they are going to somehow do something on these rows and columns to verify that everything is good and consistent. So in this case, when the verifier has this YR and WR prime, it is going to be able to kind of use those along with some sampled rows and columns of this encoded matrix to prove to itself that the received rows and columns are good. So let's call this non-interactive proof part, and then let's call this interactive sampling, which is going to be the verifier samples rows, columns of X. And then finally, the verifier check is, let's call these XS are the S rows, and X, let's call it Y S prime are the supposed columns. And now so why do I write X and Y here is the verifier actually has no idea whether the prover has actually committed to the same matrix transposed, right? So it is going to, by virtue of performing some checks, it is going to have to prove to itself that XS and YS prime do actually come from the same matrix. And that is actually why you need the two different proofs, YR and WR prime, and with different randomness. So how's the verifier going to do that? Well, the verifier is going to check. YR is the unencoded matrix times the randomness. And X is supposed to be the encoded matrix, right? So what is the verifier going to do? Well, it's going to check if the encoded matrix times the randomness is consistent with the encoding of the randomness, right? In other words, the unencoded matrix times the randomness. Encoded, right? So specifically, what are we actually checking? We're saying look, if X really is G times, X tilde, right? Then surely it is the case that G times G times X tilde times R equals G times YR, right? Because this is exactly how we defined YR, right? YR is supposed to be the unencoded matrix times some randomness, right? And so certainly if these two things are consistent with each other, then it must be the case that if we look at some, and this is supposed to be X, so this is X times R, right? Right. So now let's just look at a few entries of this, of both the, the left-hand side, which is X times R, and the right-hand side, which is G times YR. We can look at a few entries by doing XS times R, right, which are the S entries. And then we can just check whether that is equal to GS times YR. Right? And all it says is cool, or maybe even a little bit easier, actually how we're going to do it in the code, although it is a little bit inefficient to do it this way, is we're going to say, look, we received a few rows of X. We then multiply those by the randomness, and that's going to be the same. If these equalities here are true, then that should be the same as encoding YR first, and then checking that those S symbols are consistent with the randomness. We will then do the same for y, or y, which is supposed to be the columns of x. Right? And then now so now this tells us that x and y really do correspond to some matrix, to some encoding of some matrix, or they are at least close to it. Finally, we have to check that these two matrices, so, and then this will tell the verifier. Verifier knows that, prover has some matrix y tilde in their head. Finally, we have to check that x tilde and y tilde are consistent with each other. Right? So how do we do that? Well, we just do the dumb thing, which is please check that yr times the new randomness equals wr prime. wr times, sorry, let me make this wr. r prime times the randomness used for yr. Right? In other words, that the inner products of these transposes are truly equal to each other in the way you would expect. And it turns out if you do all of these checks, we do all of these checks, then verifier is convinced that x tilde exists, is consistent, and rows, columns received are good. Rows S, columns S prime are good. Okay. So that's the high level pseudocode. I know we went through a lot. It's not super interesting. I mean, they're kind of just doing only two operations and they're just checking their consistency, but just why ZODA works. And it works for exactly the same reasons that if you're familiar with Ligero, Ligero kind of gives you some guarantees which can then be strengthened to these guarantees and so on and so forth. Okay. So with that, let's add one more library, which is we need, I believe, binary Reed Solomon. And then we can add a batch Merkle tree, which is going to give us the Merkle tree proofs that we're going to use to make sure that the rows that we get are good. Okay. So how do we actually do this? Well, let's start coding. So the first things is let's just add, what do we call this? Binary field or something? I literally always forget binary fields. And then batched Merkle tree or trees? Batch Merkle tree. Great. We are then going to include / let's make a new file, and let's call this ZODA prover. Cool. All this does is literally copy pastes the inputs, this file into this module context, so it doesn't do anything magical, and that's how we organize things in Julia. And then we can just start with, the basics. So start with a commit. 2 rows. I'm just going to call it commit, actually, because I like that better. And then we're going to have some data, x tilde, as promised. And let's say we have an implicit thing called rate. I'm going to do this, or let's call it inverse rates, which we will use for the encoding. And that should be it. Okay, so with that, we already are using encoding. So so first of all, let's remind ourselves how even this stuff works, and by ourselves I mean let me remind myself how the hell this thing works. So we have binary Reed Solomon. Let's see, let's first make a Reed Solomon code, which has, let me see if I remember what the input arguments are, because I do not remember what the input arguments are. Cool. So RS is going to be read Solomon. Read Solomon takes in a type, which is going to be the field. So binary LM, let's say 32 for now. The message length, which is, let's say, going to be 2 to the 10, and a block length is going to be 2 to the 12. Right. And, okay. So this gives us an object which should perform read Solomon encoding. And we should, give, let's say we have a vector which is of size 2 to the 10. So binary LM32, 2 to the 10, right? And then we should be able to just encode, let's say encode RSV or something. And that gives us an encoded vector of size, 4x larger, so rate 1/4. In other words, a vector of size 2 to the 12. Let's just double check that. Log 2 of length of v. Great. And then let's call this vnc. And this should be log 2 of length of vnc, which is 12. So we're good. Okay, so how are we going to do this? Well, we need to commit to two things. We need to commit to the rows, and we need to commit to the columns. So we need to first encode the rows and then the columns. So I'm going to do it in the dumbest possible way for now, but then I will ideally improve that. So let's just, I guess, do it. So calls should be map. So let's make this rs equals nothing. Just for now, if and rs equals, that is just not right at all. That is, well, just not, none of that is correct. Okay. It's going to be L type X tilde, and let's do, so first things first, let's check n prime equals size of X tilde, and then let's just assert that n equals np. Nice. And then we need to initialize the read Solomon. This just ensures that it's a square matrix. Doesn't really have to be square for data availability reasons, but it's just nice when it is, because otherwise you end up with like weird, annoying things in the middle. We're going to make the message length n, and then we are going to do inverse rate times n. It's going to be the block length. So that's going to be after encoding. We're going to blow up a thing of size 2 to the 10 to a thing of size 2 to the 12. So, okay. So for the columns, let's start with, let's just map. For now, this is super inefficient, but that's fine. Actually, let me do it this way. Cool. And then we're going to map this. So each column is going to get mapped to this. So this is anonymous syntax, anonymous function syntax that says take argument C, pass them to whatever is after this block. And then we can just do each column of X tilde, which is great. And then for fun, if we do @show xcols, this should work. So let's export functions. So export commits, great, and then we should be able to just use commit on first let's do X tilde equals rand binary LM32 of 2 to the 10, 2 to the 10. Right, so we're just going to use this as our little testing matrix, and we should be able to do commit of X tilde, and it should not work because I have not imported ZODA tensor. Ooh, okay. Let's see, why are you being a pain in the ass? Let's see. Actually, do I even have revisions loaded? Yeah, I do. All right, what the hell is the problem here? The problem with live coding before you've, like, you know, done the whole setup in a while. Why are you not revising? Here, let me really quickly do this. I should be able to do commit, so. Okay. I don't know what the hell was going on previously. Oh, my G. That's a lot. Great. Glad we can all agree. That worked, I guess. A lot of elements are currently being printed. Oh, no. Please, no. So this returns an iterator. So, okay, so very quickly, what are we doing here? For each column of x tilde, it does exactly what you expect. It returns an iterator over all the columns of x tilde. We just run the encoding function on it, and then this runs a map over it, which is just what it normally means. So actually, we can even reduce this, if we want to be very Julia-esque, to this. And then all it says is, okay, cool, xcalls now is going to be like a thing which encodes all of the columns. And so actually, if we run it now, this will actually make the correct things match. So let's write this as xcalls equals and, right? And now if we do size of xcalls, it should be exactly what you expect. Ooh, no. It'll be a list of things, which is actually quite annoying, and then we can do something like hcat with this to concatenate these things, which is cool. It's a little bit slow, but that's fine. So now we have a matrix of the correct size, which is, namely, you take a column of x, you encode it, and then you just kind of put it all into like one big matrix, and that's your new matrix. Okay. So this is the encoded rows. Now let's do the columns. Or these are the encoded columns. Now let's do the rows. So to do that, you kind of do exactly what's expected, which is you are going to vertically concatenate an encoding of each row of xcalls. Right. And let's return x for fun. And from that, we should get. So anyways, now you can already start seeing why Julia is quite nice. Here, let me do this hcats. This it's very annoying, but it's fine. Julia is already quite nice because, like, look, you know, we start with some matrix, right? We apply this operation, which is like over some random binary field that Julia doesn't know anything about, except we just define it over some nice little types, right? We can then use like all of our nice little utilities to say, okay, cool, like this thing is obviously a matrix of some types, whatever it is, doesn't really matter. We then encode each column of those things. We concatenate it into one big new matrix. Then we do the same thing again to get x. And with that, we get the final result, which is a 4096 by 4096 matrix, which has the right element type or whatever. Okay. So that is, you know, our whole first part of the encoding rows and columns of this. Now we need to commit to the rows and columns of this to get the Merkle roots. So here I am going to trust that everything works out nicely. So this commit will return two objects. One for the prover, which will be like, cool, I need to open up some operations over this x and have the Merkle paths inside of it, and it will return another object for the verifier, which will be the verifier commitment, which will just return um, two Merkle roots, right? Which would be one over the rows and one over the columns. So I'm sorry, I have not been looking at the notifications or chat. So cool. Okay. So, right. So with that, let's do some stuff. Let's see if I can remember how to use batch Merkle tree. So batch Merkle tree has some functions. We actually need to refactor this guy pretty substantially at some point, but for now, we will do what we can with what we have got. So we get a build Merkle tree, which takes a bunch of leaves. This spits out a complete Merkle tree from which we can get the Merkle root. And then via the complete Merkle tree, we can provide some queries, which then get constructed into a batched Merkle proof, which is just treat as some abstract object. Cool. Okay, so let's hope all that works. Let me just make sure I am not missing something right now, although I will have to pause the stream in a sec because I need to go eat in like 30 minutes or so. All right, so cool. So yeah, I mean, also what's funny about all this stuff is like you can make a big deal out of it, but fundamentally it's all like 3 lines of code or something, so, which is kind of great. All right, so let's do this commitment. We would like to first build a Merkle tree. So, and this should just be each call X. So this will be call Merkle, and then each row. I hope this works. Let's actually test it before we do that. So if we do build Merkle tree, each row of X. Oh, oops. What did I call this thing again? Let's call this commit X tilde for now. So the cool part also, if you notice, actually, I realized I didn't say how like neat this is. I'm changing code here, and I'm just like running it on the REPL. So what's happening is the REPL is actually keeping track of what changes I make on any file and automatically like re-evaluating things that have changed, and otherwise things that have not changed just simply stay the same. You'll see this is a very common pattern. So I'll change stuff here, right, which is like in a file, and the REPL will already know what things are happening. And if you notice, I'm not like re-importing any files or anything. It's just like keeping track of the underlying structures and things that are really actually the functions. The structures are actually more annoying, but the functions that I'm changing and recompiling them on the fly as necessary. So it's like a weird thing where I use the REPL as my way of essentially roughly figuring out what I want to do next, and then kind of progressively add to the function that I am working on as necessary. And so there's no like need to kind of stop and recompile and do all of this stuff. You just kind of like fully in the flow, although it's a bit hard for me because it's hard for me to get in the flow while also speaking, which is very funny. But fully in the flow, you are doing stuff on the function, which is going to be kind of your like real source of truth, and then you're doing stuff in the REPL, which are kind of like the experiments that you get to run and or APIs that you get to mess with and make sure how to think about this. So yes, I agree. I'm glad that this is like, hopefully it makes sense as to why this would be very painful to do in Rust kind of as it stands today, unless you essentially construct very, very general levels of abstractions around rings, and then from rings you then go to fields, and then from fields you then go to like, and then what do all of these, you know, concrete instances mean of these things are actually quite complicated as well. So just, it's rather complicated to do, and actually you can do it, but I would only do it for like very special circumstances in Rust. You know, when we know the binary elements are going to be 32-bit size, and we know the extension fields to be 128-bit size, and we know like what rates we're optimizing for and all this stuff. So, okay. So let's get back to it. So x tilde. Okay, we have this. It's pretty slow right now, actually. You know, it shouldn't be this slow, but I'm doing zero optimization here. We're doing like these concatenations of all of these vectors, which are like doing, I mean, we can check actually quite how slow it is. Let's do benchmark, which will be very depressing. We're also not parallelizing this over anything right now, although I will parallelize it in a second. So this is all single threaded, and parallelizing it will not take very long, but and yeah, we see, I mean, the operation right now is insane. It takes like 1.7 seconds or something, and it allocates like 180 megs or something insane. Like, this is ridiculous, right? I mean, if we actually compute the size of the matrix tilde x, oops, it's really not that many. You know, it's 2 to the 20 elements, so, and each element is 32 bits, which is 4 bytes. So, you know, this is 2 to the 22 elements. That's what, 4 megs or something. 4 megs, but we're allocating 181 megs. So obviously we're doing all sorts of nonsense right now that is kind of totally unnecessary. But this is just for fun, and I'm just showing like how one can quickly do stuff. We'll parallelize this, which will reduce the 1.7 seconds by 8. So that's going to be like 0.2 or something. Yeah, and then we will also do more interesting stuff where we won't be allocating all of this stuff, which clearly is a lot of memory pressure. Okay. So let's continue. So we have X now. Let's actually build a Merkle tree. So we can do Merkle tree each row X. I think that would probably work. Neat. Look at that. Great. So we have a Merkle, you know, what do we call this? Merkle row, right? And that gives us some proof. So we can check what type of, you know, Merkle row, right? And we see it's a complete Merkle tree. And from there, we should be able to get root. So we get root of, you know, Merkle row, right? And we get a Merkle root here. And similarly, we should be able to get depth or something, Merkle row. And this is, it tells you that the tree is exactly what you would expect. You know, we're committing to this matrix. Started as 2 to the 10, it got expanded to 2 to the 12 on each side. We then commit to all the rows, so there are 2 to the 12 of them. In other words, the depth of the Merkle tree is 12. Okay. So yeah, so that's pretty easy. Let's say Merkle row is simply, you know, what do we call this thing again? Build Merkle tree. So build Merkle tree. Great. Each row of X, and then Merkle call is just the same thing, but each call of X. Right, great. And we can, so let's do, for now I'm going to make it super ugly, but let's return a tuple, which is for the prover. Is going to be a tuple of X, the Merkle row and the Merkle columns. This is a complete Merkle tree. And then for the verifier is simply going to be the headers of each of these, which will be get root. I'm going to get super cool and Julia. I'm just going to get root dot. And then Merkle column, or instead of row, as we did it here, and then cool. And so now if we do the whole thing, you know, if we say please commit to x tilde, and let's say prover stuff, verifier stuff. So this just simply ANS is a shortcut for the previous answer in the REPL. So prover stuff we can see is, you know, is a thing of length 3, which namely contains X, the Merkle row root, and the Merkle column root. And then verifier stuff is simply a two-tuple which contains the root for the Merkle rows, the Merkle columns. Very neat thing that we note is we can check what the verifier stuff size is. So if we do this, oops. We know that it's 32 bytes for the verifier stuff here and 32 bytes here, so the total size is 64 bytes. Obviously because SHA-256, over 8 is 32 each. So good. And then we can check what the size of the objects is of the pre-row keeping in its head, but that doesn't really matter too much. Okay, so now that's our commit function. I mean, that's the whole thing. So now let's start, although I don't know if I will get to end to do this, but the point is, like, I mean, look, we spent all this time talking about it, but like 99% of the time was like figuring out what we needed to do, and then this is the entire code for the whole thing. So, okay, so let's do the, proof. Let's say, non-interactive proof or something. I don't really know what to call this. Yeah, let's call it encoding proof for now. So what is this going to take? Well, it better take x, tilde, and then randomness, and then r prime. And what is the encoding proof going to be? Well, the encoding proof is going to be the dumbest possible thing you could think of, which is literally going to be, please return that. Even the AI got it perfectly. Great. So now if, let's say r is going to be a random. So actually, it's not quite right yet, but I will make it right in a second. It's going to be a random, binary LM. By the way, here's where it gets interesting. So what's very important is that, this thing here that we're running, this thing is over binary LM32. Right? But in reality, for good soundness, we actually need the randomness to be drawn from binary LM128. Right? So that's already very magical, right? Because x tilde is a thing. I mean, if you look at the L type of this, so the element type of x tilde is a binary element 32. Right? Yet r, we're going to draw from binary element 128. Let's do 2 to the 10 for now. Right? So what the hell are we going to do here? Like, I mean, this thing is like, these are two totally different fields. Like, and, Rust would freak out if you even thought about this. For fun, let's just do this. Right? Let's just multiply this. And that's perfectly reasonable, perfectly, totally, nicely defined. So what just happened, right? Like, we wrote a very innocent thing which says, okay, please multiply a 32-bit field element with a element of, 2 to the 128. What's actually happening is this thing is, the only thing we did, which I will show you in a second, is we showed Julia how to embed the 32-bit field element into the 128-bit field. Right? And in doing so, every time that Julia gets arguments that are inconsistent with each other, it knows that it can essentially upconvert or upcast or whatever. And it's not quite upcasting, but it's something similar-ish, to the 128 field by this natural embedding, which I will show you what it is in a second. And then just do the multiplication in the 128 field case. So to see this, how do we do it here? We do binary field. And the way we define it is very, very simple. It says convert. So the promote rule says, okay, take any type that's binary element. For any binary element, we have only really defined the largest field to be binary element 128. So it just upcasted automatically to binary element 128. So that tells you how the types upconvert, right? So it's good question when I say this. So it is explicitly defined in the promote rule here, but it is inferred in the sense that Julia knows whenever you type an operation or an operand, it will try to promote everything to like the thing that it needs to be. Think of like the types form a lattice, like a lattice in the join and sense, right? So in other words, they are like a DAG, right? And then the question is, what's the smallest element which all elements have in common? So in other words, what is the element lowest in the topological order, right? Or in the level in this like partial order, such that every element is either that element or points to that element, right? And Julia just automatically infers that pretty easily. So it says, cool, okay, now I have an element, like now I know what type I need to convert things to, right? Via this like, just like, you know, least upper bound type thing. And then you have to specify how to actually convert the element. And that's very easy because what we do is we just do a standard embedding, which says take a root of the polynomial, the irreducible polynomial over f2 to the m. So in this case, let's say it's f2 to the 32. One of the roots is this one, which doesn't really matter. And then do the obvious thing where you just take the powers of that element, and that's your embedding. How we get that doesn't really matter. I'm happy to like draw it out at some point later, but it doesn't really, it's not super interesting. But the point is like all it reduces to is a bunch of bit shifts and a bunch of XORs or binary additions or whatever we want to call it. Okay. So that's everything that's happening there is just happening under the hood. Oh yeah, and for context here, this at generated essentially means like you're not running this every time you're running this thing. This actually is a function which compiles the code, right? Because Julia code is itself editable by Julia before it is compiled. So we actually compile code. We compute these variable or these betas outside of the loop. That gets compiled down to code, which is simply like a constant array here. So these betas, like, you know, this is the beta element, which is the generator of the subfield, which is consistent with the like irreducible polynomial over the big field. We then just define this vector bs, which are the b's, the betas, and then all we do is just take powers. So beta 1 is 1, beta, or bs1 is 1, bs2 is beta to the first power, bs3 is beta to the second power, which is just this. And then the only thing this thing does is it just like spits out, instead of computing this every time you call convert, it'll simply spit out the array, right? So it runs once and you're good with the given arguments. And then the rest of the function, all it is just some unrolled loop that gets unrolled via LLVM magic, and we're all good. So it's pretty neat. But anyways, all that is happening under the hood. Like, you don't have to give a shit about any of this stuff, right? Like, I just typed, you know, binary LM128 times like something, and it just like does the right thing that you expect, and we're all good. Okay, so to really show you that we're actually all good here, is, you know, we'll just, cool, here's the encoding proof. Let me export that too. So we do encoding proof, and we do like ZODA, and let's say R. And let's just do R again for fun. There you go. Works exactly as you expect. And that's our encoding proof thing. Great. So we've already fixed this. We fixed this. Now we need to do the sampling. So it's so far pretty good. I mean, like, look, you know, just how many, we have 22 lines of code and we've already finished our prover. So I think that's pretty cool. Let's do the verifier, right? So verifier is going to take, so we're going to take, you know, let's call this verifier info. Right now, this is I should make this all in a struct, so I'm not really going to do that right now because it's kind of dumb. But verifier info will be a tuple of two things, and we will like deal with the mechanics later. S and S prime, which will be the subsamples that we get, and we need the verifier commit, verifier and proof, then SS prime. Okay, so the verifier commitment is Merkle root, Merkle row root, Merkle column root, verifier commit. We don't need the two. The verifier encoding proofs, call this YR and WR prime as we did here. There we go. Great. And then we have these S and S primes, which are going to be, for now, let's assume S and S prime are in sorted order. So, specific, what are we going to do? Well, oh, right. We're going to also need to get S opening roots. Let's call this opening. Right, and so we're going to get S opening paths. Opening paths. Great. Cool. So let's first things first. Yeah, check the Merkle roots. Wow, you really did it. Look at that. Oh, right. Merkle openings, and then or Merkle. Merkle proofs. And then let's call this opens. And then row XS YS prime equals opens. Okay. Let's see. How do we do this? So let's first just do the batch Merkle stuff. I'm a little bit worried about because I need to make sure that everything is right, but let's just do the linear algebra part first. It's kind of, funnily enough, would be the hardest part to do in pretty much every other language, but it's very easy to do in this particular language. So what is the check that we need to do? Well, the check that we need to do is XS times R, is that equal to the encoding of YR evaluated at S? Right, so and let's call this R and R prime. Obviously, this is like insanely silly. Like, this whole thing is ridiculous because in reality, we should be encapsulating all of this stuff in a bunch of structs. But for now, I'm just doing the obvious dumb thing. So let's do that. So we're just going to do the dumb thing first to start, which is XS times R had better be equal to, right, and then just let RS in it. Again, all of these things should be encapsulated in some struct, which keeps track of the initialization and then keeps track of the verifier commitments and the encoding and stuff. I'm just like fully like zero good vibes, like all just full sending it on this entire bit. Okay, so for now, let's just assume that we have the same parameters here. Assume we actually need RS in it. So we're going to pass that in too. And then what we're going to do is we're going to say, cool, please encode YR, and then beautiful. Look at that. Even the AI god knew exactly what we needed to do. That's pretty much it. So that's that. We're going to do the same thing. Actually, let's even do this. If at error. There we go. And then same thing here. Just to be more specific. Okay, this should be YS prime times R prime. This should be WR, right? WR prime. Great. And then let's see what the AI god says here. Great. Okay. And then let's try this out. So if we did verify, we don't need the verifier commitment. We do not need the verifier. Oh, we do need the verifier encoding proofs, actually. So let's copy this. YR, WR prime. And then let's call it encoding proof equals YR, WR prime. Oops. Verify encoding proof. Okay. So where were we? Let's do verify. Oh, we need s, so let's just make s and s prime the same. Let's just, for now, I'm just going to do some random numbers, like 1, 32, 45, 100 or something. Great. And so, by the way, just for fun, I mean, it's very easy to do something like x of s, comma, whatever, in which we'll return, oops. I have x. Oh. Wait a minute. Right. So this is verifier or prover stuff. 1 is going to be x. So let's call that. And then let's do x of s sub s, and it does exactly what you expect. Right. So as you would kind of think is like, cool, you have like x. You want to get the s rows of x, just simply, do the thing that you would expect, which is please get me the s rows of x. So we have s here, just define it randomly. Let's call xs is going to be x s comma colon, and then we'll do the same thing for y. So what do we call this? Y s prime is going to be equal to x of colon comma s or something, which are going to be a 4094 by 4 matrix. And let's give this version. So, great. Okay, so now we should be able to call verify as it stands today. Oh yeah, I guess, sorry, for context, let's just even check this directly. We have this, so we might as well just check that this indeed should hold. Oh, crap. I've been switching between 2 different keyboards for annoying reasons. Oh my god, unbelievable. So I am like totally actually screwing up my layers. So, okay, this should be access times r. Vector b has length 124. That's good. Okay. What is r? Right, so it's not xs, sorry, it's x tilde s. Right. So it should be x. No, this should be right. xs times r should return a, right, we need to get the first quarter of xs because this is already, the whole thing is fully encoded. So I did screw up a little bit, so this is 2 to the 10. S 1 to 2 to the 10. And binary. Right, rs is going to equal read Solomon binary 32. 2 to the 10, 2 to the 12, just for now. And cool, we're good. It looks like our checks have passed. So, okay, sorry. Okay, so what the hell did I do here? XS is a fully encoded matrix. I actually made a mistake here. In reality, we're not checking that x times r is equal to this. We're actually checking the first half of the element. So 1 to 2 to the 10 are actually, or whatever. I mean, 1 to, size, or like size of x, x tilde 1 or something is equal to this. Just because what you actually want is you don't want the, if we look at x is not g times x tilde, it's actually g times x tilde times g prime transpose, or times g transpose if we're using the same code for both ends. But this has an identity as the first block, so that's what we're going to use to check that everything is good. And so we end up with this interesting bit here where we have xs is equal to the encoding, and it's exactly what you'd expect. Multiplied that by the randomness is the same thing as the encoding first and then S. Also, this looks very innocent, but it's actually really not, right? Encoding here was defined for binary LM to the 32, which is cool, except for the fact that YR is not a binary LM to the 32 thing. It is actually a binary LM 128 vector. So that's already another problem, right? If you, again, were to do this in Rust, like, you're going to have a lot of problems doing these, like, explicit up conversions and down conversions. But the point here is, like, again, by just having defined the right types and the right, like, way of putting everything really into kind of one big field, you get exactly what you expect, which is namely that encode of Reed-Solomon of YR actually does do what you expect it to do. So with that, I think I am going to take a quick break. I'm going to go grab some lunch, and I will be back to finish up the verifier in a little bit. Thank you, everybody who's joined so far, and yeah, hopefully it's at least been a little bit enlightening and or fun. And if not, then you don't have to watch it. It's fine. I won't be sad. I mean, I'll be a little bit sad, not super sad.